Okay, so the next proposition tells us, like by the notation so far, let di denote the degree of pi, where pi is a place in the curly p we fixed in the beginning. And let k be the greatest common divisor of the all degrees. Here you shouldn't confuse that like this, the k is the rank of, and this is not the rank of, and this is the greatest common divisor. And let h be the class number of f, then function field lattice is a sublattice of an minus 1. So they recall that an minus 1 denotes the hyperplane lattice. So that means this is the integer lattice. So the entries should be integers, where the sum of the coordinates are equal to 0. So that means we want to see the same property for the function field lattices, for the vectors in the function field lattices. And the second property tells us the rank of delta p indeed n minus 1, but it doesn't mean that they are going to be the same. Let us recall that the rank was of the hyperplane is also n minus 1, but this is not going to be the case because, like in the third property, we will see that, like if we treat them as like the additive groups, then the index of the function field lattice in the hyperplane lattice is given by the product of the degrees of the places we consider over their greatest common divisor times h0, where h0 is a positive integer that divides the class number. So as long as it is not equal to 1, we can see that they are not going to be the same lattice. And the determinant of delta p can be computed as the square root of the length, again, times the degree of the places we consider over their greatest common divisor times h0. So like this index times the square root of n gives us the determinant of the lattice. Again, h0 is a positive integer which divides the class number. So let's try to investigate the first two items in this video, and then I will give the proof for the third and the fourth one, at least sketch of the proof. And for the first one, what we want to see is that like the coordinates, like the vectors in the function field lattice have this property, right? Just because, recall the construction, which is given by mapping z to vp1 z degree p1, vpn of z degree pn. Always like all entries are integers, right? Because we know that discrete valuation map is defined from the function field to the z union integer, and here let's say we have that like the zeros and the poles of z indeed is a subset of p, so we don't have any infinity, and so that means they are integers. We also know that the degree of the places are the extension degree, so they should be also integer. And the second property we need to verify that the sum of the coordinates should be always 0. And that this is the fact because we know that like some are okay, some of the coordinates might be 0. We are not going to wonder about it, but for the support of its principal divisors, we might have non-zero entries. But I mean, all zeros and poles should appear in the set of P, right? So this expression indeed is the same thing, the degree of the zero divisor or the pole divisor. Indeed, it's I'm sorry, it's indeed the degree of the principal divisor, and principal divisor are degree zero divisor. So this is why we have this equality. And for the second part, what we want to show is that rank is n-1. So I mean, we need to find n-1 many linearly independent vectors in our function field lattice, right? And to be able to see that, as I mentioned in the beginning of today's lecture, let me consider the divisor di times p1, di times p1 minus d1 times pi for I from 2 to n. By the exercise, we know that the divisor h times di p1 minus d1 times pi is a principal divisor. Here h denotes the class number. And if we consider, like, if they are principal divisors, right? So that means there exist the functions that such that principal divisor of z is exactly h times this divisor. And obviously this function is element in OP star, right? Because it has, like, okay, this is h times this divisor. This is obviously in the OP star because it's, when we look at its support, like, so that means it has 0 at P1 and it has pole at Pi, and by the choice of the P and Pi, these are elements in the curly P. So this is the function in OP star. So we can talk about its image, and when you look at its images for the places in the curly P, whenever P is equal to P1, its image has the first coordinate as h times d2 times d1 minus h times d1 d2, and the other coordinates are going to be 0 because their valuation, like, is going to be 0 for this divisor. And for the rest of the divisors, we can, like, by the way, we need to compute degree valuation of z at p1 times degree p1, and as we compute these quantities, we will get, like, the vectors hd1 hd2 d1 minus hd1 d2 0, h d3 d1 0 minus h d1 d3, and the remaining coordinates are 0, h d and d1 0 0 up plus coordinate h times d1 dn, and all of them are contained in our function field lattice. So here we have in total n-1 vectors, and this is going to be your exercise question. These are linearly independent over R, linearly independent vectors over R. So that means rank of our function field lattice is n-1. And the proof of the part 2 and 3 is a bit tricky, but it involves like important tools. So this is why I want to explain, and see you in the next lecture, in the next video. Bye-bye.